Okay, so how are you doing? So what I'm going to do is I'm going to relate the concepts of unit cell structure to uncertainty principle and the velocity of sound and XRD. It won't all be on the same video because I can't make long videos. All right. So let me just start. I'll begin with the fact that a lot of times you would like to think of atoms as being spheres. All right. Now spheres and being in an array of other spheres. Okay, an array is just when they're side by side. The examples that I give you today will deal with the square array setup. Okay, they have other, it's like when you can draw a square as far as layers are concerned of your atoms. They have other forms of arrays, and this is like a close pack array. I'm not speaking about that, but I'll be speaking about this one. Okay, so with atoms, many times you can relate them to what's called a unit cell. Like they have all these layers, and you could apply to those layers a unit cell. What's called a unit cell. One of the most simplistic forms of a unit cell is a cubic unit cell, and that's pretty much just a simple cube. All right, and this particular cube is a primitive cube, so I'm going to call this like prime C, primitive prime C. And this, you could also have arrays of these. Okay. So, okay, now with that, with this array, this is one form of a cubic cell, unit cell. Now, another form, this is a primitive form, another form would be a body-centered cubic. Okay, BCC, body-centered cubic. And that would have a cube structure, but in this structure, what you have is a point in the center. Now, what I mean, you may not see this from the board, but here's like a jar, right? Here's a jar. And there are things inside of the jar. I put a point here, but this point is supposed to represent a point within the cube, inside the cube, and it's at the dead center of the cube. All right, body centered. Now, with this body centered, a lot of times it's represented with like an inverted pyramid, four-sided pyramid, above an upright pyramid. And usually that's done just to give you an idea of how it's conformed, how this point is conformed inside of this cell. So so this is like this top layer here, that's what this top layer is here. The base layer is like this base layer here for the cube. Alright? So that's the body center. Now let's say this point here you can infinitely divide this point. You can keep taking a point from this point and doing whatever with it. Okay, now if you take this point and pull it to the face, if you were to take this point and pull it to the face of this cube here, and pull it to the face, this face, pull it to that face, every single face, if you pulled it to the face, what you would end up is a face-centered cubic form, where every single face in the cube has a point at the center. Okay, pretty much. And so it's basically like there's a face and then there's an X with a dot in between. There's like 6 times of those. All right. So these are like some of the basic forms of a cubic structure. And many times you want to calculate what's called a packing ratio. All right. Now, to do that, you start off with a 2-dimensional representation many times. So a 2-dimensional representation, let's say of the BCC and even the FCC, at this point where I draw this here, it's a 2-dimensional representation. At this point, they look the same. All right, now here's where they differ, because this diagonal line here, this is called a body. For the BCC, it's called a body diagonal. Okay, it's called a body diagonal. And what that means is it's pretty much this line here. You see where I have this, it's that line. You see how it goes from one side to the other? Basically, here's like this Kim White box, right? Is if I took a straight rod and I placed it right through this point here, the rod should come out at this point. Okay, so basically, if I took this box, I could like spin it. I could like spin it on that rod. That's the diagonal. That's the diagonal that this diagram here is representing. Okay, just to give you a perspective of both of these. Now the diagonal here is a face. It's a face diagonal. It's a face diagonal, and with the face diagonal, this diagonal here line is pretty much representing this face of the cube. So you can pretty much, let's see, let me draw it again. So if you were to extend this unit cell out, basically you'd have another atom there and another atom here. So it's kind of like you're extending it. This would be like the back portion here. This face here would be this face here in the back. So that's what this diagonal is extending for. And I'm just doing this to give you a perspective of the unit cell. At every sphere, right, there's a radius. For the body center, there's a radius. BCC equals a square root of 3 over 4. That's what the radius equals. And for the face center, it has a radius, and the radius FCC equals a square root 2 over 4. All right. So now you want to calculate your packing ratio, and you usually start off here. Okay, get your radius, and the packing ratio formula is the number of atoms times the volume of your circle, or your sphere, I mean, the volume of your sphere times 1 over A. Now, this A here is due to the fact that you have A in the radius. Alright, and you guys already know the concept behind A. You know, I don't need to really break that down, especially even with the numbers of atoms in each unit cell. For a BCC, there's 2 atoms in a BCC, in a BCC structure, unit cell, and the 4 atoms in FCC. Alright, so if you wanted to say PFCC, okay, the number of atoms is 4 times 4 pi over 3, and the radius for the FCC is a square root 2 over 4. I think you can see this, yeah. And that would be cubed times 1 over A, 3, A cubed. So the A cubes cancel out. Those will cancel out. The A's, there's 3A, the A to the cube, A cubed, I mean. 4 to the 4 cubed is 64. 4 times 4 is 16. 16 divided by 64, that's like 1 over 4. Alright, but this square root 2, if you cube square root of 2, you end up with 2 square root 2. And so if you have 4 here, 2 divided by 4 is 1 over 2, and then you have 2 times 3, so what you're going to end up with is a packing of this expression, square root of 2 over 6, and that would equal 0.74, around that. Okay, the packing ratio for the FCC is 0.74. Now for the packing ratio, let's say for the BCC, down here, BCC, 2 atoms, 4 pi over 3, radius a square root 3 over 4 cube times 1 over A cube. Alright, so what you would end up with is pi over square root of 3 over 8, and that was going to equal 0.64, a value of 0.64 of the packing ratio. Okay, so basically that's how you would calculate your packing ratios for specific unit cells. Alright, and let me continue this on another video, because this is already. I don't know how if this is going to upload or not.